Good morning, good afternoon, and good evening to all those listening in. Today I'm going to be talking about how to build rate 1/3 non-malleable codes. This is joint work with Divesh Aggarwal, Bhavana Kanukurthi, Lakshmi Obbattu, and Maciej Obremski. Let's head into the talk by first looking at what non-malleable codes are. They were these cool primitives introduced by Obremski, Petrzak, and Wicks at ITCS 2010. Like any coding scheme, they consist of an encode algorithm that takes in the message and outputs the code word C, which is prone to some form of adversarial tampering attack. So the adversary can pick some function f and modify it to a C prime. In the subsequent slides, we'll see what kind of tampering is actually allowed, but for now, let's say it's modified to a C prime. And this we decode to recover the modified message M prime. The kind of non-malleability guarantee that we seek is that such a M prime will either be same as the original message M, which is kind of like an error correction feature. But if such an error correction is not possible, then we seek that the M prime turns out to be independent of M. We'll formalize what this independence means in the next slide, but this is informally what non-malleability means here. In addition to this, we also seek the standard correctness feature from any coding scheme, which is that if no such tampering occurred, the decode of C should give me back the message M with probability 1. So how do we formalize this non-malleability? We have this code word C. Particularly, I'll tell you how to define this non-malleability for the specific kind of tampering model that I'll be focusing on in this talk today. And the model is called a split state model. So particularly here the code word has two parts, a left and a right part, and the adversary is allowed to pick two arbitrary functions f1 and f2 in such a way that f1 acts only on L to give you L prime, f2 acts only on R to give you R prime. In other words, you allow tampering of two parts of the code word arbitrarily but independent of each other. This is called the split state model and would be the focus of our talk today. Under such a tampering attack, let's say you recode and recover the M prime, I'm going to define this distribution on the recovered M prime by this tamper random variable, which if you notice depends on the message choice M and the functions that the adversary picks, which is f1 and f2. So to capture independence, what I would give you a guarantee under this definition is that there exists a simulator distribution which only depends on f1, f2, such that regardless of the choice of M, so for all M, the tamper random variable turns out to be statistically close to the simulator random variable. So why does this definition capture independence? What I'm saying is that while the actual tamper random variable depends on the choice of the message, of course, I can actually simulate it using a statistically close distribution which only depends on the function choice and not on the message, and hence is actually independent of the message M. So this is the kind of non-malleability guarantees that we seek from the NMCs. Where are these actually useful? Where is such a tampering model actually useful? So specifically the split state model that I defined, the non-malleable codes against them turn out to be useful in several crypto applications. Just to list a few of them, they are useful in building non-malleable commitments, non-malleable secret sharing, domain extension for non-malleable encryption, and privacy amplification, and more recently to black box 4-round pairwise MPC in the plain model. Each of them is independently a very interesting primitive in the crypto realm, and I urge you to look at these papers to see how actually split-state non-malleable codes turn out to be useful. So having looked at a formal definition and what non-malleable codes are, and having seen why they are useful in several crypto applications, let's come to formalize the parameters of interest with regards to them. While we already sort of saw them through a glimpse of the definition, let's be a bit more formal. So the two parameters of interest here are the tampering model and the rate as for any coding scheme. So let's look at them one at a time. First, let's talk about the tampering model. So I already defined our non-malleable codes for what is called as the split state model. So particularly I looked at the code word as two blocks. But to be more general, This family comprises of generically a T-split state model. So in other words, I can split the code word into T separate blocks and allow tampering of each of them arbitrarily but independent of each other. So this is just extending upon the two block model that I defined. So this is the formal description of the function family. And if you notice here, if n is the code word size, then the value of t can range technically from 1 all the way to n. However, t equals 1 means you're allowing tampering of the whole code word arbitrarily. And this is too strong a model to hope for non-malleability. And this was in fact officially shown in the first paper and is quite easy to see. So t can only range from 2 all the way to n. The observation to make here is that lower the value of t is, more powerful the adversary is. So in other words, for the lowest value of t equals 2, which is what we saw the definition for, would mean you're allowing the adversary to actually arbitrarily tamper half of the code word. And this is the most powerful adversary you can hope for in this realm. Coming to the second parameter of interest, which is rate. It is officially defined as the message length to the code word length ratio. And particularly if you notice, this measures the redundancy that you introduced into the code word. And higher the rate is, lower the redundancy introduced, which is what is desired. You do not want to blow up the code word size by a lot. So having defined the two parameters of interest, a long-standing open problem in this realm has been to build optimal rate codes against the strongest possible tampering family here, which is the two-split state model. And this is the goal that we set to achieve through this talk. So let's move on and look at what has been the state of art in trying to achieve this goal. So I told you that our goal is to build optimal rate non-malleable codes. So the first natural question is, what is the optimal achievable rate? And this was given due to the feasible result of Chiragji and Guruswamy at ITCS 2014. What they prove is that for any T-split state scheme, the best achievable rate is 1 minus 1 over T. So particularly this means for the two-split state model that we are interested in, half is the best achievable rate, and hence that's the target that we set to achieve. Having said that, the initiation for building such codes started with the first work of Zimbowski, Kazana and Obremski at Crypto 2013, and they gave the first explicit construction, although which worked only for 1-bit messages, and the rate achieved by the scheme is omega 1 over n, where n is the code word size. So this is an inverse polynomial rate scheme. Subsequently, this was extended to give a more general construction for arbitrary messages. So this was the first explicit construction for arbitrary messages due to Aggarwal, Dodis and Lovett in STOC 2014. And the rate of the scheme is omega 1 over n to the 4 by 5, again inverse polynomial, through the sequence of optimizations. And both these constructions rely on similar proof techniques, both of which are non-trivial. And particularly the arbitrary message construction requires additional complex theorems from additive combinatorics. The point to note here is that this construction line has inherent limitations in improving the parameters because of the complex proof technique that are used in. And hence, we land up at a question of seeking alternate directions to build non-malleable codes that give us potentially rate improvements from here on. And that is what led to the another beautiful connection of non-malleable codes, which was established by Chiragji and Guruswamy in 2014. They define these primitives called non-malleable extractors, which are interesting on their own, and they show how building such non-malleable extractors will directly give a construction of non-malleable codes in the two-split state model. This led to a series of works that actually aim to build non-malleable extractors with better parameters, and all of them turn out to have complex constructions, and the best possible rate in this realm is due to Shinli in 2019, which achieved a rate of omega log n over log n. So this brought it down from an inverse polynomial to a logarithmic rate, however, because all these constructions of non-malleable extractors are complex in themselves, improving the parameter further on became challenging. And particularly, I should mention here that the same work of Shinley in 2019 has a constant rate scheme, but the error here is constant. And in crypto applications and in any of the setup, we are always interested in negligible error. So once again, we land at a point where we are seeking for alternate routes to build non-malleable codes that potentially help us get the rate that we want. This brings us to the third beautiful connection that was established in this work due to Aggarwal, Doris, Kazana and Obremski at STOC 2015. So they introduced this new proof technique slash construction technique called non-malleable reductions, and through these technique they build non-malleable codes which actually achieve rate of omega n to the minus omega 1, which is the inverse polynomial. However, in the same work, they do conjecture a constant rate scheme via this route. Indeed, this is the technique that led to the first explicit constant rate scheme. So this was due to Aggarwal and Obremski at Fox 2020. And like I said, using these non-malleable reductions, they get the first constant rate code. And the constant here is 1 over 1.5 million, which is huge. And particularly this construction turns out to be quite complex, and the proof techniques are also quite complex. And what they call as these non-malleable reduction is a step-by-step process, and every step of it incurs a loss in parameter, which is kind of not salvageable. So further improving on this constant rate it turned out to be almost impossible to do, which is once again led to the question of finding out newer techniques to build non-malleable codes that potentially lead us to our final target. And that brings me to this work of ours, which builds 1/3 rate non-malleable code, thus improving on the rate prior rate by a huge factor and giving us a near optimal rate. And we managed to do this via a new proof and construction technique called rate and non-malleability amplifiers. We'll get to what this particular technique means in the future slides, but this technique was sort of used by Kanukurthi, Obbattu and Sekar through their previous works, which aim at actually building non-malleable codes for higher state tampering models, but we use it in the setup of 2 split state model. And turns out, in addition to getting such a huge rate improvement, our construction is also simple, so is our proof. So with that target and premise set, let's head in to look at how we actually build these rate 1/3 codes. And for that, I have to first start with telling you what our building blocks are. We require 3 building blocks, all of which are simple. So the first building block that we seek is our information theoretic one-time message authentication codes. Particularly, they are just schemes that generate signatures of messages using some key, and we only require a one-time authentication property, by which I mean that for any information theoretic adversary, so an unbounded adversary, that just observes a single message tag pair, it should be impossible to forge a tag on a fresh message. So it's just a one-time authentication feature I need. The second major building block that we need are strong randomness extractors. They are primitives introduced by Nissan and Zuckerman in 1996 and independently have been a massive object of interest in the pseudo-randomness literature. Particularly, we are interested in a version of them called seeded extractors. So particularly here, the extractor function takes in a source which is picked from an entropic distribution W, and with the aid of an additional string which is picked from a uniform distribution and is of a short length called seed, the extractor is able to output a string Y which actually looks close to a uniform string. So a bit more formally, what this means is that the extractor output turns out to be close to uniform even given the seed distribution and some additional information on the source W. Of course, this additional information FW that we give is such that the entropy of W should still remain high given this F of W. So all this is saying is that the extractor manages to spit out a random string from an entropic string using the aid of a short uniform string, which also turns out you can give out and open. Besides this, the third building block we need is any of the two split state non-malleable code which I listed in the prior works with poor rate. So this is the sense in which I mentioned that we are going to build rate and non-malleability amplifiers. Which basically means that we'll start with any of the poor rate two split state code. And the catch here is, since we are using any of the poor rate codes to make any progress in amplifying the rate of the scheme and to use the non-malleability of the scheme, we'll only use this to encode short messages. And hence the rate would actually be beneficial for us. Okay. So we are now ready to set forth and to see how our construction works. And before heading into the full-blown two split state construction, let's start with the warm-up scheme, which works for a 4 split state model. This is due to Kanukurthi, Obbattu and Sekar from TCC 2017. So here, the construction proceeds as follows. To encode the message M, the first sort of step we use is to mask this M using the tool at hand, which is the extractors. So particularly, we pick the source W, the seed S, and we XOR the message with the extractor output to generate the ciphertext C. So we output the ciphertext in separate state and the source that we use to generate the extractor in a separate state. So C and W are output out and clear. Since they are output and clear, for security reasons which we'll get to later, we need to also authenticate these two strings. So we pick KW and KC, the authentication keys, and generate tags TW and TC on W and C respectively. We'll output TC along with C and TW along with W. So those are my two states. Additionally now, I also need to convey the seed S along with the authentication keys for us to be able to decode the message. And for this, we will use the underlying non-malleable code. So we are going to encode the seed and the two keys under the underlying non-malleable code NMENC to get the two states L and R, and we output L and R. So this is my complete code word: C, TC, R, W, TW, and L. And this is sufficient for me to recover my message, if you notice. The point to note here is that the underlying non-malleable code is only used to encode short strings. Particularly the seed and the authentication keys are all only logarithmic in the message size and hence do not play a role asymptotically in the rate. So let's look at how this warm-up construction guarantees non-malleability. So particularly we are allowing each of the 4 states to be tampered by the functions f1, f2, f3 and f4 as shown here. So what do I need to show to prove non-malleability? I need to show you how to build a simulator that just depends on f1, f2, f3 and f4. And to get the non-malleability, like I said, we are going to amplify the non-malleability of the underlying NMC. So we would use the underlying non-malleability, which tells you that there exists a simulator that just depends on f3, f4 and gives you the tampered S prime, KW prime and KC prime, which are one of the two. So one of the two cases can arise with respect to these. Either they'll be same as the original or they will be independent. This is the guarantee that the underlying NMC gives. So let's look at each of these cases separately. In the case where they are same as S, KW and KC, we will end up using our authentication property because if C prime was not same as C or if W prime was not same as W, then my max security will guarantee straight away that the adversary could not have forged valid signatures on them and hence you would always output bot. Thus, in this case, you cannot have this, which means that there was no tampering that occurred and hence your output would be M. So this is how we handle the same case. Coming to the independent case, which is the major part, we are guaranteed here now that the S prime is independent of S, and this is where we will use our extractor security. So in other words, the extractor security would guarantee that the extractor output on W and S turns out to be close to uniform even given the extractor output on the modified W prime and S prime. Why is this so? Because this extractor output on W prime and S prime is just a function of W, as S prime is independent of S. So this is just a pure extra information, which is f of W, which we can give. And the length of it can also be tolerated under extractor security. So having this security, what is in turn guaranteed is that the M prime, which is just the extractor output on W prime S prime, XORed with the modified C prime. This M prime is independent of M. That's what is implied by this. And this is what gives us the non-malleability feature. So good, we have something which works for a 4-state scheme. But turns out when we go to the 2-state world from here, things get much more challenging. And our final construction for the 2 split-state scheme is the exact same encode process. But now we allow tampering of R, C and TC together and L, W and TW together. And as soon as we merge these states and allow the tampering of them together, things become way more challenging. Particularly, to list one of the key challenge, we face problems in proving independence. And particularly the reason here is that the extractor security can no longer be used directly. Why is this so? If you observe, the information that we were additionally giving out was extractor output on W prime and S prime, right? But now this information depends on C through F2, because tampering of R also depends on C. And because of this, it in turn depends on extractor output of WS. So this information is no longer just a function of W, but also a function of the extractor output on W and S. And turns out such an information can be catastrophic and break the extractor security. So we can no longer use extractor security directly. And how do we resolve this? Well, on a very high level, we do this by breaking the correlation that exists here through the ciphertext C using a Markov style argument. So a little bit more elaboration on it. What we do is, as a first step, because the dependence through the C is the problem, we consider a random C tilde, which has nothing to do with the message, and use that to proceed on with the rest of the generation of the tampered distributions as before, but using C tilde instead of C. And turns out the C tilde, the extractor of W prime S prime, where S prime is now dependent on C tilde and not C, and extractor of WS form a Markov chain. This is easy to see. And now because I've gotten rid of the dependence on the actual C, I can use my extractor security as before and give out this extractor of W prime S prime. Now the tricky part is to bring back the correlation, and turns out what we can show here is that this closeness holds even when we condition all of this on the fact that C tilde is the ciphertext of the actual message. So in other words, we are able to prove that C tilde is close to uniform given the extractor output W prime and S prime, even conditioned on the fact that C tilde XORed with extractor output is M. So this is in turn meaning that C tilde, from being random, you brought back the correlation. So this only, I just wanted to highlight one of the key challenges. Of course, in the full proof, we have several other challenges to meet with regards to other cases in the simulator. And I refer you to our full paper for the same. So in summary, I showed you that how to build our 1/3 rate non-malleable code at a glimpse. And this is a link to our full paper, which you can refer to. Thank you.